Okay, let's go ahead and now work out the remaining questions in this problem. So, the second question is, what is the voltage across R1? All right, so let's draw a bit of a little zoom in diagram here. So we're looking at R1 here. Okay, and so what I'm going to do, I will draw a little picture. There's our R1 value, so there's our R1 resistor, and it's 200 ohms. We know it's 200 ohms. We know the current leaving the battery, we know what that was, we calculated that, but we also know all of it will go through R1 because R1 is in series with the battery. So the current going into that resistor, R1, is going to be 0.042 amps. And what we want to do is work out the voltage across that resistor. And therefore, because we're looking at a specific component of the circuit, we're going to use the local version of Ohm's law. So V equals IR, but remember with the local version, V is the voltage across the component, I is the current through the component, and R is the resistance of the component. So in this case, V will equal, the voltage across the component will equal the current through it, which is 0.042 amps, multiplied by the resistance, which is 200 ohms. And so that will be, from calculation, that will be 8.4 volts. So we know the voltage across this resistor, the R1, will be 8.4 volts. Okay, let's put that in. So V1, which is the voltage across resistor 1, is 8.4 volts. Okay, let's clear that. Okay, so we've done this one, we've done this one. What is the voltage across R2? All right, well, if you remember back to Kirchhoff's laws about voltages, you might remember that the net voltage around a circuit must equal 0. Or put another way, if this 12 volts is the voltage lift of 12 volts, then we must have a total of 12 volts in voltage drop in any given loop around the circuit. Now there's more than one loop in this circuit. Now the one that we're interested in is the one which contains R2. So let's trace out that loop. So we're coming out of the battery, we're going to go through R1, but we're going through R2 and then back to the battery. So there's our loop. So the total voltage drop around that circuit, the total voltage drop must add up to whatever the voltage supplying that loop is, which is 12 volts. So R1 I'll call it V1 actually. V1, which is the voltage drop across resistor 1, plus the voltage drop across resistor 2, which is V2, must equal 12 volts. But we already worked out the voltage drop across resistor 1. Here it is here. It's 8.4 volts. So we know that's 8.4 volts. So V2 must be 3.6. So this value here has to be 3.6 if they're going to add up to 12 volts. I'll put another way, V2 will equal 12 volts minus V1, which is 12 minus 3.6, which is, 8.4 that should be. 12 minus 8.4, which will equal 3.6 volts. So we now know the voltage across R2. It's 3.6 volts. So let's put that on a little chart here. So the voltage across R2, which we'll call V2, equals 3.6 volts. Okay. Final question, what is the current through R3? Okay, now, once again we go back to Kirchhoff's rules. The current coming out of the battery will all pass through R1. However, when it reaches a branch, remember Kirchhoff's law says the total current going into a junction, there's our junction there, will equal the total coming out. So whatever current's going in, some will go this way and some will go this way. And in fact, more will go this way because there's less resistance this way, so more current will go this way. However, this current in this branch here and this current in this branch here must add up to whatever current that was feeding that branch was. So the current in, and we know that current in, which is 0.042 amps, then these two currents in each of these branches must add up to 0.042 as well. Okay, so we have to decide, well, if we can work out the current through one of them, we can then work out the current through the other. So which of those two resistors do we know more information about that we could actually work out the current through it? Well, we've just worked out the voltage across R2, and we know the resistance of R2, so that would be our candidate. So we're going to work out the current through R2 first, and then use Kirchhoff's laws to work out the current through R3. So once again, we're going to be using the local version of Ohm's law on R2, and this time we want to work out the current. So the current, remember the local version of Ohm's law, the current is the current through the resistor. V is the voltage across the resistor, because we're using the local version, and R is the resistance of the resistor. So the current through that component will be the voltage across R2, which is 3.6 volts, divided by its resistance, which is 500. So 3.6 divided by 500 is 0.0072. And so that's the current through R2. But the question's asking for the current through R3. Well, remember, the current through R2 and R3 combined must add up to 0.042. Okay? So, in other words, current in that junction, this junction here, must equal current out. So therefore, 0.042 must equal the total amount of current coming out, which will be what we just worked out, which is 0.0072 plus the current through resistor 3, which we'll call I3. So therefore, I3, which is the current through resistor 3, will equal 0.042, take away 0.0072, and if we work that out, we will have an answer of 0.0348. Now, what I haven't been doing here is expressing these currents in probably a more convenient form. Normally, if currents are this small, we'd express them as milliamps. So 0.034 amps, in actual fact, would be 34.8 milliamps. Okay? So we've answered all those questions. And you can see that this is a typical example of where we put everything together, our understanding of series circuits, parallel circuits, Ohm's law, and we can use that information to basically work out any current, any voltage, and any resistance in a standard circuit like this. Okay, thank you.